Software Engineering Radio, episode 108, Simon Peyton Jones on functional programming.
This is Software Engineering Radio, the podcast for professional developers, on the web at se-radio.net. SE Radio brings you relevant and detailed discussions and interviews on software engineering topics every 10 days. Thanks to our audience and the partners listed on our website for supporting the podcast. Welcome listeners to another episode of Software Engineering Radio. This is another episode on languages. We're recording this at QCon, and thanks to Microsoft once again for giving us this room here. This time we are talking to Simon Peyton Jones. He is a believer in Haskell, as I learned this morning in his talk. So we're going to talk about functional programming, Haskell, and related topics. So Simon, welcome to the show.
Thank you very much.
So why don't you introduce yourself to our listeners, personal background, where do you work, what do you do?
I work at Microsoft's Research Lab in Cambridge. I've been there for about 10 years now. I work in the Programming Languages group. Before that, I was a professor at the University of Glasgow. I was there for 10 years. And before that, I was a lecturer at University College London. For 7 years, and before that I spent 2 years in industry, and that made me realize how hard all you guys work. So I thought I would get a job in a university instead.
Yeah.
So now my job's programming languages research, and so I get to study more or less what I like and publish very freely. So that's a very exciting job to have, but it's not to get access to Microsoft's developers. I talk to them quite a bit, but also I can work on things that are not directly related to Microsoft's products at all. Yeah.
One example for that is Haskell, because I think it's not a Microsoft product, or is it?
No, Haskell is not a Microsoft product.
Okay.
Alas. It's so I've been interested in functional programming ever since I was an undergraduate. In fact, when I first did a short course on functional programming, I became addicted to the incredible elegance of writing tiny functions that did awesome things.
Yeah.
So ever since then, my research has really been focused around turning functional programming into something that moves from being a clever idea into something that you could use in the real world.
Right.
And as a vehicle for that, I was involved in the design and development of this language called Haskell, because quite a few, this was the late 1980s, quite a few of us were working in different research labs on non-strict or lazy functional programming languages, but we all had a different one. So then we all got together at a conference and said we should have one language. So then we met, and over several years we developed this language called Haskell that is now like 15 or 17 years old.
Okay.
So it's quite a mature language.
Yeah.
And it's developed quite a bit over that time as well.
So one of the hallmarks of Haskell, as far as I understand it, is that it's one of the few really pure functional languages. So why don't you explain what functional languages are in general, and especially what makes them pure and why this is important?
A good way to start is to think about a spreadsheet. When you write a spreadsheet, you write formulae that compute the value of a cell from the values of other cells. And in a formula, you wouldn't write in cell A2, you wouldn't write equals print something followed by 3, because you wouldn't know when that would be executed. It would be an odd thing to do. Yep. So the formulae in your cells simply compute values from other values. It doesn't make sense for them to do anything else. And in the context of a spreadsheet, we don't question that. So that's what I mean by purity, in which functions compute values from their inputs, and they compute a result value.
Something you used this morning was to contrast the imperative style, which is location-oriented or location-based, with the value-based approach in functions.
Right. So in an imperative program, the way an imperative program works is the program counter moves down one statement at a time, and as it moves down, the values of mutable locations change. So a location called X is not the name of a value. X is the name of a location whose value changes over time. Whereas in a functional language, if you have a variable called X, it's the name for a value. Anywhere that X is in scope, it has the same value. And that's quite a big shift in programming paradigm. Indeed, when you first hear about this, if you've never done any functional programming before, my first question was, when I was thinking about this as an undergraduate, is can you write any useful programs at all in such an emasculated language, right? One that does not even have an assignment statement. An assignment statement is the very fabric out of which we build. the programs that we're all used to.
Yep.
And the amazing thing is, yes, you can.
Although handling state and side effect is an interesting topic there, which we'll discuss later, I guess.
That's right, yes.
Yeah. What I hear often in the context of functional language is the Lambda calculus. Can you maybe say a couple of words about that?
So I suppose the Lambda calculus is to functional programming as, the x86 or z80 is to imperative programming. So the Lambda calculus is kind of like the most boiled down version of functional programming you can imagine.
Mm-hmm.
So the Lambda calculus is a tiny language with only 3 constructs: variables, Lambda abstractions, and application. So it's just got 3 syntactic forms and 1 reduction rule. And yet you can translate monstrously complicated Haskell programs into this tiny calculus. And then you can watch the tiny calculus executing. So you could almost think of the Lambda calculus as being like the execution mechanism for a functional program. It doesn't actually happen like that, but it's not a bad way to think of it. So the Lambda calculus is the essence of functional programming in an incredibly small space.
You already said that there is this idea of applying something, applying a function to a bunch of values, resulting in a new value, which you can then use. So having values as part of functions is probably clear to everybody who has seen functions in math. But in functional programming, functions are also values.
Right. So the question is, what kind of arguments can a function take?
Right.
So we're used to functions taking arguments that are integers or floats or perhaps lists or trees. We're not quite so used to them taking arguments that are functions. But after you start to think about it, if you have you may find yourself writing the same pattern again and again. So supposing you find yourself writing a function that doubles every element of a list, and then later you find yourself writing a function that trebles every element of a list or reverses every element of a list. Well, then you think, maybe I could just write one function that does something to every element of the list. And what's the something? Oh, I'll pass that as an argument. What does that mean? I'm passing a function as an argument. Another even easier example, filtering a list.
Right.
So if you want to take a list and you want to say, give me all the even elements, then what do you want to give to filter? You want to give it a predicate function, that is a function from list element to bool.
Right.
And it applies that function. So it's very natural to want to pass functions as data, and that's something that's called higher order functional programming, and that's something that any functional language allows you to do. So it's also possible to do this in conventional mainstream object-oriented programming languages these days. They're usually called delegates.
Right. Yeah.
And delegate is just a kind of function that you can pass as an argument.
Yeah. One thing that became really crystal clear in the slides you've shown this morning is that because functions are the essential building blocks of a functional language, they require very, very, very little syntactic overhead. So it really reads very elegantly. And for example, currying doesn't require any special thing. You just call a function with only one argument, and that implicitly returns, assuming it had several before, the curried function. So this is really nice.
Right. There's quite an economy of concept there. That a function of the way you mentioned currying, which some of your listeners may not know about. But the idea in its essence is pretty simple. It says a function of 2 arguments. You can think of it this way: it's a function that takes 1 argument and returns a function of 1 argument, which returns the final result. So take the addition function. The addition function, if applied to an argument 3, a single argument 3, returns a function. And what does that function do? It adds 3 to things. So there we've, as it were, boiled down. Instead of having multi-argument functions, we can now have single-argument functions. And in fact, in Haskell, it's true to say that every function only takes 1 argument, but it can return a function which takes another. And it turns
there
out
is sugar that you can actually pass several. Oh
yes, of course. So when we write f space a, we mean f applied to a. When we write f space a space b, we mean f applied to a applied to b. So function application in Haskell is left associative.
Is this also how it's implemented literally? Or is this just a metaphor to think about it? Or
it's how you think about it. It's not, no. So in the actual implementation, inside our compiler for Haskell, we do some analysis to say, this function actually can't do any work until it's given 3 arguments.
Okay.
So we'll implement it as a piece of machine code that demands 3 arguments. If it's given fewer, we'll save them up somewhere.
Okay.
And arrange to give it to them later.
So if we talk about the philosophy of Haskell being a pure language, then I guess one of the really, obviously, important building blocks is the side effect freeness of it. So
that's what purity means. Yes.
Exactly. So can you elaborate a little bit about what side effects are and especially why they might be a problem?
So what's a side effect? So a side effect is when you call a procedure and it does something other than transform its arguments into a new result value. So there's something other that it might do. It might write into mutable state, persistent mutable state.
Mm-hmm.
It might do some input. It might take some input for read the disk. It might delete files. It might launch missiles. It might. So a side effect is in fact anything other than returning a result that's computed from the inputs. Now, why are these bad? Because after all, that's what imperative programs do all the time.
Right.
In fact, you see many procedures which have a void result type. You see void f of ABC.
Yeah.
And so the only reason you call it, right, is to have the side effect. Right. But you're not interested in the result. It's void. After all, you know what it's going to be.
Yeah.
So why are side effects bad? Well, let me instead say, why is purity good? So at the moment, side effects are so much part of the fabric of our present languages that it's hard to see how you could do without them. But let's imagine that you could work in a pure language. Then what would you get? So one thing that's very helpful is programs can become easier to understand and reason about because there's less happening behind the scenes. It can also be easier to maintain. So when I make a change to a function, that usually changes its interface. Right. So when I change its interface, I change its type. And now the compiler tells me there are lots of other places I need to change. If instead of changing the interface of a function, if it still has type int to void, but instead it modifies one more or fewer global variables, then it's harder to see what consequent effects there might be. So maintenance tends to be a bit different. Testing is different too. If you want to test a side effecting function, then what do you have to do? You have to set up the state of the world to be ready to call it, inspect the state of the world, and see if the expected state change has taken place. So, and by the way, you might have had to copy bits of the initial state of the world first, so that you can compare them before and after.
That's where mock objects come in, right? Where you can replace parts of the real world with simulated parts to achieve exactly this goal.
Right. And it's not that it can't be done, but that it's a bit of an uphill struggle. And if we could do without it, this would be good. And we can do it in a pure world. If you could work in a pure world, this would be very nice. Because what do? Well, you can test a function simply by giving it some test values as its input and looking at its output.
Right.
So if you're testing the sine function, you give it 0.1 and you look at the output, and you give it 0.2 and you look at its output. There's no state to set up. There's no state there's no old and there's no new.
Right.
If you're testing the set union function, you don't need to worry that set union will modify the input set. Just compare the input set with the output set. So testing is particularly easy, and in fact that leads directly to better automation. So there's some rather nice testing tools available for Haskell. One of which is developed by some colleagues of mine. It's called Quick Check. And it has a rather beautiful property that you just tell me the type of a function. You tell Quick Check the type of a function, and it'll generate random data suitable for functions of that type and give you some test some of its properties. That's rather remarkable, and it's because all the interface is on the surface. Another reason you might be interested in purity is that it gives you a better handle on parallelism. It doesn't make parallelism easy. But it kind of makes it, feel a bit more within reach. In a imperative programming with mutant side effects on global variables, it's hard to put your hand on your heart and say you're sure that this thing is thread safe.
Right.
You use locks and condition variables, and you hope and pray, and you establish rules and invariants, and it's very difficult to get right.
Right.
In a purely functional world, it's actually very difficult to get wrong, right? Because your programming is kind of inherently, you don't have any locks and condition variables because there's no mutable state to lock.
Right.
That said, it's not true to say that you can just press a button on a functional program and it'll run in parallel, because for a number of reasons. One is that the data dependencies within the program might sequentialize it.
Right.
And so if you think about its data flow diagram, it just might not be parallel at all. Less obviously, even if it is quite parallel, it may be difficult to get a sufficiently large level of granularity to execute efficiently. So I don't think it's parallelism without tears, but it kind of gives you a chance in a way that the imperative by default with shared mutable state makes things very difficult.
Since you don't have mutable state, recursion is something that's used quite a bit.
Right, so recursion effectively replaces iteration.
Right.
Because iteration relies on going around the same code with the same locations with different values, and so if you don't have mutable values, that kind of iteration doesn't work. So yes, recursion replaces it.
And there are a couple of optimizations to make recursion feasible performance-wise. I think you mentioned two this morning in your talk. Obviously, one is tail recursion, and the other one is lazy evaluation, or memoization, I think you called it. So why don't you elaborate a little bit on those?
Tail recursion is the one that you must do to if you're to reasonably claim to be able to execute arbitrary programs with the same kind of asymptotic efficiency as you can with an imperative program. So all tail recursion means is if a function calls itself, or indeed any other function, and that's the last thing it does, so sort of f of x is, if something, then f of x prime, else something else. So the last thing it does is to call itself. Then instead of calling itself or the other function, and then when you come back from that, removing the current stack frame, you remove the current stack frame right away. So it's an implementation thing, but it's important because it means that when you do something that amounts to a loop, just do something 1,000 times, you don't grow stack that's 1,000 deep.
Right. No.
So in practice, that turns out to be very important. And any Haskell implementation will do that.
Okay.
It's a little tricky if you're compiling to .NET or to the JVM. If that's the target of the functional language implementation, then you have a tougher time because those language platforms don't support tail recursion very well. They do somewhat. Actually, .NET does reasonably well, partly because there were some functional programming types involved when .NET was being designed. However, what your other point was lazy evaluation.
Right, exactly.
So lazy evaluation, I think, is not fundamental to purity. You could have so lazy evaluation means that when you call a function, you don't evaluate its arguments before the call. Instead, you pass to the function a kind of suspension or thunk or recipe.
Closure?
A closure,
right,
yes.
Just to get the term.
That's right. Yes, or closure. So there's multiple names all for the same idea. You wrap up the argument. You don't compute it in advance, you wrap it up, and then if the function inside itself ever needs the value of that argument, it pokes on the thunk, or closure, or suspension, and that causes it to then do the computation. The computation is delayed. That's called laziness, or call by need, or call by name. As distinct from call by value, which is the normal way that Lisp or indeed C# would work.
And of course, that's important for an if statement, for example, because you want to evaluate only the then or the else part. So that's where it comes in.
Yes, that's a good point. So if you want to implement if, not as a language construct, but as a function,
what
just another function, yes. Well, so in Lisp there's cond, you see, which is a language construct pretty much.
True. Right.
Or maybe it's a macro or something. But it's not just an ordinary function, because an ordinary function in Lisp would evaluate
it's a special
its
form.
argument.
Yes.
So in a lazy language, you really can implement if just as a function.
And you had this morning that you showed how to implement various control structures for forever.
That's a little bit different to lazy evaluation. That's more to do with this monadic side effecting stuff.
Right. Well, later.
Which we'll get to. But so laziness is a distinctive feature of Haskell. Right? There's not very many lazy functional programming languages.
Okay.
So it's one of Haskell's distinctive features. And actually, it's the reason that Haskell has stayed pure, because if you're going to have a lazy language, that means that a function may evaluate its argument at some time that perhaps is a bit hard for the caller of the function to know. That's really to do with the implementation of the function, right? When it evaluates its argument. So if its argument was to have side effects, then it'd be hard for the caller to know whether the side effects would take place at all, and if so, in what order relative to everything else. So what that means is that it's much more it's much less reasonable to just say, we'll allow you to do side effects after all inside these quotes functions than it is in a call by value language. So in effect, Haskell's laziness, which I think is a super property, I really love programming in a lazy language, but in the end, when push comes to shove, the important thing is purity.
Right.
And laziness is a kind of helped us to stay pure, but and it's wonderful in itself. But it's not mine. That the high order bit is be pure.
So the other thing you mentioned this morning was this memoization thing, that a function that's called several times as a part of a recursion tree only is executed once, and the return value is cached to optimize performance.
No, I shouldn't. I hope I didn't mislead you into thinking that will happen automatically. It's not the case the implementation behind the scenes is going around looking for every call and saying, oh, have I called that function with the same value before?
I was actually misled. And you know why? Because I'm involved with a tool for model-driven software development, and we have a somewhat functional language in there, and it has exactly that feature. If during one basically execution of a script, you call the same function several times, it's actually only ever evaluated once. It's very useful for graph transformation.
Yes.
So, and I kind of related that to this memoization you mentioned this morning.
Well, that's a perfectly sound implementation, but it's quite an expensive one to apply to every function all the time.
Yes.
Because it means you have to retain all old function calls and their results forever.
Yes, and that's not what we do. It's only for create functions that actually create new objects. Because, I don't want to get into this.
Yeah.
It's useful in practice for graph transformation.
Yes, so I can imagine in particular circumstances. And it'd be very nice to be able to point to some function and say, memorize this one.
Exactly.
It does interact with laziness too. If you haven't evaluated the argument yet, you might be applying it to 2. You might be really saying f of 2, but it's f of something which evaluates the 2. But you haven't evaluated it yet.
Yeah.
So anyway, the point is that you might want to do a static transformation, that is a transformation at compile time that transforms an inefficient program into an efficient one by gaining extra sharing. This is really what dynamic programming is about, and that transformation is justified by the side effect-free nature of the calls.
Right, because you can, it's safe to do these things.
That's right.
So we said, or you said, that the core abstractions in functional programming languages are obviously functions. So what's the role of data types? Do you have classes? I mean, how does that go together? I mean,
data types are terribly important. So we define new data types all the time.
Okay.
So they're typically what's called algebraic data types. So you say the way you do it is you say, here's your new data type. I'll call it T, and it has constructors A, B, and C. And A has 3 fields, an int, a float, and a bool, and B has no fields, and C has 1 field that's an int.
Yep.
So you'd write, so data type T is A of int, float, bool, or B, or C of float, something like that.
Yep.
Now, those A, B, and C are called the constructors, so it's pretty similar to an object-oriented language with an abstract class T and 3 subclasses, final subclasses A, B, and C.
Yeah.
Right? So then you can build values of type T by using A, B, and C as constructors. You can say A of 3 true 4.0, or just B, or C of 3.0. Those would each build a value of type T. But you can also use them in pattern matching, right? So then you say F applied to open brackets A of XYZ equals, and so that says F applied to that kind of pattern. Does this answer? F applied to B, does this? F applied to C of something, does that? So you define functions by cases.
Right, so just to connect to a previous episode, we had in Erlang, we also discussed these things.
Right.
Erlang has this too, and also in Scala.
Yes. So in Erlang, you don't declare a new data type. You can just do this pattern matching thing across, any in a more freewheeling way.
Yeah.
So that has advantages because it means that you can. Sometimes untyped programming is very convenient, but if you're writing a function and you say, it's quite nice to be able to say, in fact, it's really helpful from a software engineering point of view to say, this F takes a value of type T. T has exactly 3 cases, A, B, and C, done. Right? I have covered all the cases.
Yep.
I know that at runtime, I'm never going to get a value that I don't recognize here.
Yep.
That's a very powerful static guarantee that you can get out of this kind of thing. So data types, very important, but they don't have the same usually. It's not impossible to do this. Scala does... Scala lifts some of these restrictions, but in most functional languages, when you declare a data type, you can't then add new constructors to it later.
Yeah.
And sometimes that's very inconvenient, not being able to add later, and most of the time it's just fine.
Yeah.
So data types are very important. Functions and data types play very nicely together.
Yeah, just in a somewhat different way than you might expect from traditional programming.
Yes. So a data type is rather a passive thing, right? So in an object-oriented language, when you declare a new class, you usually give it behavior.
Right.
So in a functional language, when you declare a new data type, I beg your pardon. When you're saying give it some behavior, then that makes it easy to add new types with the same operations. But adding a new operation, of course, is a bit more difficult. This is the standard sort of trade-off that lots of people have discussed, but I'm sure most of your listeners will be familiar with this. But functional languages tend to, the shoe is on the other foot. It's inconvenient in a different way. Right? You have a data type. It's easy to add new functions over that type, but it's not so easy to add new variants of the data type.
Yeah.
And people have tried quite hard to build languages to support both. and that's it's a very worthy endeavor, but not something that's I don't know. Nobody's found anything that's completely satisfying yet. I think Scala is probably one of the best instantiations of such an attempt.
Yeah. Okay, so let's talk about side effects.
Right.
Or maybe not talk about them because we don't want them, or maybe still talk
we
about
want them sometimes, don't
right,
we?
that's exactly the point, because writing a piece of software that has no side effects, as you said this morning, will heat up the CPU and don't do anything
but nothing
useful.
else.
Yeah. So we clearly have to deal with side effects somehow.
Yeah.
So why don't you give us an overview of how you resolve this tension between not really wanting side effects, but somehow having them and maybe managing or containing them.
Right. For a long time in Haskell, it was we were very pure and also rather embarrassed because we had a purely functional language which couldn't do very much because it had these essentially no side effects. So the whole program was a function from type string to string. But that led us to eventually to develop this idea which is called Monads.
So that was originally, this is a part of, it was invented by the Haskell group.
Absolutely.
I didn't know that. Okay.
Yeah. It was Phil Wadler at Glasgow, where I was a professor, remember?
I see.
In the early 90s. And so Phil has a brain the size of a small asteroid, and he was good at maths and category theory too. And he spotted these very clever but deeply obscure papers by Eugenio Moggi, who's an Italian, with very small glasses, smaller than yours. There's little small round glasses. Brilliant guy. And Phil understood Eugenio's papers and said, I could write a program that does this. And then I looked at Phil's work and said, we could use this to do imperative functional programming, to do side effects inside a Haskell program without polluting the whole language with side effects everywhere. So we wrote this paper called Imperative Functional Programming, which turned out to be the start of a really interesting development of figuring out how to mix side effects into a purely functional setting without throwing the baby out with the bathwater. So the way, briefly, that it's done is the side effect bits and the pure bits are kept apart by the type system.
Okay.
So a function with type. In my talk this morning, I gave the example of a function called toUpper, which has type string to string.
Right.
And it converts a string to uppercase. Its type is string, arrow, string. So you know that it doesn't do any input-output. It can't do anything else. It takes a string, it delivers a string, that's all. But if you see another function, getUserInput, whose type is string, arrow, IO of string, so you should think of this in the same way as you might think of string arrow list of string or string arrow array of string. Yep. The IO of is a type constructor of some kind, like in generics. Right? So string to IO of string. Now that IO thing says, here some input output might happen. So it says, get user input says, give me a string and I will give you back an IO computation. And an IO computation is something that can do some input output and then return a value of the given type, the string in this case.
And because it's a part of the type system, the compiler can know about it and not apply all those reordering and other optimizations, because that would be dangerous here.
That's right. That's exactly right.
You know what this reminded me of when I was thinking about this stuff this morning? It's a little bit like the volatile keyword in C, which basically says, don't touch this, don't optimize this, because this variable to which the volatile is attached is modified from behind your back from the operating system or somewhere. Of course, it's the other way around. It's not the program outputs, it's something changes the program. But it's basically a hint at the compiler, don't mess with that. Is that fair to say in some way?
Yes, that's true, but it's much less draconian than that.
Okay.
So if I have a function of type string arrow IO of string, for example, it's perfectly okay for me to inline that function. The function is still a pure object, so I can inline it. I can move the function around, and what else can I do? I can store a value of type IoT in a data structure, or pass it as an argument to a function, or return it as a result. It's a very first-class value.
Yeah.
So in fact, the compiler. So I would imagine I've not seen the implementation of volatile.
No, neither have I.
But I'm guessing that there's a lot of ad hoc jiggery pokery to switch off things when there's a volatile kicking around anywhere. But with this monad stuff, it's much simpler than that. So what happens inside our compiler is that as far as the compiler is concerned, something of type IoT looks very like a function from world to a pair of A and world, right? Mm-hmm. So one of these computations is represented as well as a function. So it's rather Haskell-centric view of the universe to say that that an I/O computation takes in the entire universe and transforms the universe a little bit by mutating one variable in it and returns a new, slightly modified universe. But as far as the compiler is concerned, that's fine. So now what that means is that all this I/O stuff is simply transformed, as far as the compiler is concerned, into more lambdas. And once that's done, it optimizes those lambdas like crazy, just like any other lambda. So in fact, it's a very, if you like, it's a very principled way of switching off optimizations. That means that 90% of the compiler doesn't even need to know there's any funny business going on at all.
Another thing you said this morning is that it's a way, or that monads are a way of classifying side effects. So do you have only the I/O monad, or are there other monads in or monadic types, or monadic type constructors in Haskell?
Oh, lots. So from a very early stage, we realized that we didn't just have the idea of the I/O monad as something by itself. We had the idea of it's almost a design pattern, a monadic design pattern of which I/O is one instance.
Right. Yeah.
And a state transformer is another instance, an exception monad is another instance. And in fact, it's not built into the language or its libraries how many instances there shall be. So this is actually directly supported in the language designed by a mechanism called type classes, which is used for all sorts of other purposes too. Type classes are a way of describing a computation pattern, a design pattern, if you like. And so the monad class in Haskell. So you shouldn't think object-oriented class.
No,
you should think something
class
more like
of types, categories.
It's more like a design pattern. The monad design pattern in Haskell then allows anybody, you, to in your next Haskell program you write, you can build a new monad that's supported syntactically by the compiler with do notation and so forth, and in which all the monad combinators, like that forever thing that I showed you and the for thing that I showed you this morning, those will work on your new monad just as they did on all the old ones.
That's the relationship to the control structures.
Yes, that's right. So what that means is that actually what we discovered is not a particular monad I/O, but rather a design pattern, and we found a way to fit that design pattern into Haskell's existing type class mechanism in what was, I don't think we should take credit for this part. It turned out to be a very beautiful way. It just fitted nicely.
Yeah. So another interesting thing you mentioned this morning was the relationship to transactional memory. We had an episode on transactional memory with, I forget what the name of the author was. There was a paper at last year's UPSLA about the analogy between garbage collection and transactional memory.
Oh, yes.
So that was actually...
It's probably Dan Grossman.
Exactly, right.
Yes.
Yeah.
Yes, he had a nice UPSLA essay about this.
Yes. So we had an interview with him. And so can you let us know the relationship between monadic stuff and the atomic keyword and transactional memory?
So here's a beautiful example of wishing to classify effects more finely than just having I/O or pure, right? Because what we really want to say is, so let's just revise transactional memory. What you want to be able to say is, atomically, do this and this and this and this, where these things are mutations of transactional variables. You are not allowed to say, atomically, do this and this and launch the missiles and do that and that. Why not? Because the transaction is supposed to execute it's supposed to be possible to execute it optimistically and then roll back and try again, right?
Yes.
So it's important that it doesn't make any commitments like destroying small countries before it knows that it's ready to commit. So it's very helpful to be able to classify the side effects, not to say it does no side effects at all, but to say this block of code, this expression, does only side effects on transacted variables. So in STM Haskell, the atomic construct, it's not a language construct, it's just a function.
Sure. Yep.
And its type is STMA arrow IOA, which means it takes as its argument a computation that does STM-like things. So a side effect in computation, but one that can only manipulate transacted variables. And it runs it atomically and delivers the result into the I/O monad, which is this richer monad. So there's a kind of stratification of effects that the STM monad has limited effects, and it can deliver its result to the I/O monad, which has lots of effects. And inside the STM monad, you may be calling pure functions that have no effects at all.
another thing to conclude this side effect discussion, I guess, is that of course, if you have a function whose return type is not IO, so it's just maybe string, and you call a function inside that function whose return type is IO string or something, then you will probably get a compile error or something. So because the compiler can check from the type system how the pollution, the non-pureness, propagates through the program.
Yeah, that's right.
It's a bit like the throw statement.
It would be like adding 3 to true.
Right.
The compiler just says type error.
Yeah.
So if you call an IO-ish function inside a allegedly pure one, type error.
Yeah.
Yes. So that does mean you get pretty robust guarantees.
Right. Yeah, exactly.
About where impurity is happening.
Mm-hmm. Okay, so let's look a little bit about the benefits and liabilities of the functional approach in general. What I saw this morning, I mean, it wasn't new to me this morning, but it was nicely illustrated also in Ted Newrot's F# talk, that the notation can become quite compact. What do you think does this mean for writability and readability? I mean, how likely, provoking, of course, so how likely is it that if you write a nicely compact function, I can understand it?
It's often the case that people say, I rewrote my program in a functional style and it became very much shorter. That's a common observation.
Yeah.
It's not invariably the case. Sometimes there are programs that just have lots and lots of things that must be done, ranks of buttons that must be arranged, and there's no way to shorten it. But it often does happen. It's certainly possible to write obscure functional programs, like one-liners. I remember when I first learned APL, I was all excited because I discovered that you could write you could write an APL program on 3 or 4 lines, but you could sometimes write the same program on 1 line, a very long line with huge intermediate arrays, and it would still work. I thought this was just the best thing since sliced bread. But my mentor at that stage, I was 18, said, doing that is like carving a piece of wire out of marble. It demonstrates your skill as a carver, but it's really not what marble was meant for as a medium, right? So in the same way, in functional programs, it's possible to get so abstract and to try to make things so compact that it becomes quite difficult to understand the program.
Yeah.
But I will say that, so I don't want to defend that style, but nevertheless, it does in practice seem to be a medium in which it's possible to build new abstractions that match your particular application. So then in effect you build up a vocabulary of functions that match your application. So now it's almost like having a domain-specific programming language.
I was about to mention that, So is there any experience specifically about using Haskell for internal DSLs?
Oh, well, for internal DSLs.
Well, building DSLs inside Haskell.
If you type Haskell DSL into Google, you'll get lots of hits.
Okay.
So one of the standard examples is of parsers. Right? So we're familiar with Yak and Lex, which let you... So they take a different language, that's Yak's input language, and transform it into C.
Yeah.
So instead, to build a Haskell parser, what you can do is you can write a library with which has a type like parser of A, meaning so a parser of A is a parser which delivers values of type A. So underneath the parser is probably consumes a string and produces a depleted string and a value of type A.
Yep.
But just think of it as a parser producing values of type A. Now you can imagine a combinator, a function that takes 2 parsers, a parser of A and a parser of B, and combines them together to make a parser of A-B pairs. What does that do? Well, it parses the A value, then it parses the B value. And then you can imagine a combinator that goes many, written star sometimes in syntaxes. So many of P means has type parser of A to parser of list of A. And what it does is it parses as many copies of A as it can and then returns them as a list. Right? So now what you find is that, so now you might want, if you want a parser for an alphabetic identifier, you might find yourself writing, alpha, then. So then is the combining form. Alpha, then, many of, alpha or num. Right. So this many and then and or are all parser combining things. So in effect, this many and or things are stuff that you would form part of the, as it were, the concrete syntax in Yak. They're just infix functions in Haskell. You can define your own infix function. So it turns out you can pretty much write down a grammar that looks a bit like a Yak grammar, But it is a Haskell program.
Cool.
So that's an embedded domain-specific language. But instead of being a domain-specific language written in its own syntax, it's a domain-specific language written in the syntax of the host language, and that's very good. If you can make that work, it's brilliant because then you get all the facilities of the host language, modules and functions to let you scale up.
And the ability to define your own new control structures using the stuff we discussed before is, of course, also a really good building block for defining DSLs.
Yeah, and in fact, parsers, you'll be unsurprised to hear, form a monad, and the same do notation and the same combinators that work on I/O computations will work on parsers too, rather remarkably.
Okay. So after discussing all these concepts in theory, let's take a brief look at the practice. Mm-hmm. So where and how is Haskell used today?
Oh, so Haskell is being used by a bewildering variety of people today. So Haskell has moved from, I would say for a long time, Haskell was used by hundreds or a small number of thousands of users, and now it's sort of sprouted by a factor of about 10, I would say, in the last 5 years or something. Something big has happened.
Is this because of the parallelism thing?
I don't really know what suddenly made this happen. It could be that functional programming has been taught at universities for long enough.
Right.
That there's even managers have heard of. It could be that Haskell's been somehow there's something in the air.
Yeah.
It may be that parallelism is helping push things over the hill, but. And what's Haskell being used for? Haskell is used by a lot of banks. People build web applications using Haskell. They build machine learning kind of applications. They build gene sequencing things. It's a general purpose programming language.
Is it fair to say that it's especially suitable for algorithm heavy stuff as opposed to, like distributed systems, web architecture, blah, blah stuff?
So yes. So if you've got a complicated algorithm with rich data structures, then it's particularly good, right? Yeah. If you've got something where the principal business is you've got to take apart an immense gob of XML, do something meaningless to it, and send it out again, or do something modest to it, right? Then it's really helpful to have really big libraries that hack XML apart. Yeah. That's the other thing that's happened in the last few years is that a lot more libraries are available for Haskell. So a few years ago, there was nothing equivalent to CPAN. Now we got an equivalent to CPAN. It's called Hackage, and every month 100 people upload new libraries. 100 unique new libraries a month go up there. Now, they're of variable quality, but nevertheless, from 0 to 100 a month is a big change. It's a sea change. Yeah. What are the implementations like? There's several different, but all open source implementations of Haskell available.
Compiler, so.
Yes, so there's an interpreter called Hugs. Our compiler is called GHC, the Glasgow Haskell compiler. Glasgow is where I was at university. Yeah. It's probably the most widely used Haskell compiler just because it compiles pretty good code. And it has an interpreter that comes with it as well. And it comes with program coverage tools and profiling tools. Cool. So it's then there's another sort of laboratory kind of compiler called NHC, which is very nice because it's much more easy to modify. It's a smaller, more manageable beast, whereas GHC is a pretty big beast these days.
Is there a relationship to F#? I overheard this morning that you're like 2 doors away from Don Syme.
That's right, yeah. So Don Syme's my immediate neighbor. He's part of the same group, and I'm just 3 or 4 doors down from him. Yeah. So the relationship to F# is mainly an intellectual one. So Don for quite a while said, Simon, come on, you get your finger out and get Haskell onto .NET. And for various reasons, that's quite difficult to do because Haskell is a pure language and .NET is not. Right. And so and Haskell needs, there's various Haskell aspects of Haskell's type system that are richer than .NET's, right? If you're prepared to adopt .NET's type system, that's okay. But unfortunately, Haskell can't adopt .NET's type system. It wouldn't be Haskell anymore. So it just was somehow not a good fit. So Don then filled that gap by saying, all right, let's design a functional language whose high order bit is it's a .NET language. All right. So now lots of design decisions are made for you. Yeah. That's really good because then you don't have to make them. Yeah. Now let's try to inject all the good stuff we can about functional programming into that. Yeah. So in effect, he's filling a different kind of niche. Haskell is playing the principled laboratory in which a lot of ideas grow. That F# recently adopted an idea called workflows, which are just monads with a friendlier name. But they came straight from Haskell, and Don is careful to say that whenever he describes them. I'm very nice of him to do so. But I think I often see Haskell as a kind of laboratory in which ideas can grow up. But it is also a practical vehicle. Lots of people use it for real applications. GXE is right up there if you look at the language shootout, which is slightly dubious dubious mechanism, but it's this sort of very crude performance comparison. It's no longer the case that functional languages lag performance dramatically.
Is there any specific language that Haskell derives from or took influence? Well, of course, all the functional stuff before it, but is there anything specific?
Oh, there were several important lazy functional languages that were around at the time we designed Haskell. So KRC was one, the Kent Recursive Calculator, and Sassel, both of which were designed by David Turner, who was a very important figure in these early 80 days of functional programming. It was his papers on SK combinator reductions that first got me excited about functional programming in the first place. So his languages, Sassel, KRC, and Miranda were very important inputs. ML was an important input, and a language called LazyML, a variant from Chalmers University. And there were a couple of others, but those were probably the big inputs. There's a paper called The History of Haskell on my homepage, actually. It was a little while ago, last year. There was the History of Programming Languages conference.
Yes. You were there.
And so we wrote so I gave a talk about the history of Haskell.
Yeah, cool.
So there's a sort of 60-page epic paper describing some of these early experiences of why the language got designed, who designed it, and why. So you can. It's an easy read, actually. And there'll be a video sometime.
And we'll put a link to that into the show notes. So last question before we finish this up. If somebody wants to learn Haskell, is there a good book? Where do you get started? How do you get started? So
the place that I would definitely start if I was learning Haskell would be to go to haskell.org. There are various tutorials. There are quite a few tutorials there. There are quite a few books. There's an older book called The Craft of Functional Programming by Simon Thompson and The School of Expression by Paul Hudak, and a more recent one by Graham Hutton called, Functional Programming in Haskell? There's a very recent book that isn't quite out yet, which actually I would think in the end might be more suitable for your audience, which is called Real World Haskell.
Yeah.
If you just type that into Google, you'll get to it very quickly. It's being authored at the moment. Various chapters are available. And you have the opportunity, if you look now, to give the authors feedback on their chapters. You can say, this part was completely opaque, or why don't you have a chapter about this? Yeah. So it's being developed in a rather open sourcey kind of way.
Yeah, cool.
But the other thing is that I would really get onto the Haskell Cafe mailing list or the Haskell IRC channel. For some reason, the Haskell community is a very friendly one. So you can ask extremely stupid questions and you get extremely quick and friendly replies. You will not get any, you idiot.
Yeah. Okay, anything else we didn't cover? Anything, any words of wisdom you want to leave with our listeners?
One reason that I came today and about the talk I gave was saying that I think that whether or not you adopt functional programming as being the way of the future under that brand, somehow or other, this business of controlling effects is going to be important.
Yeah.
And if it's going to be important, then it's a good idea for professional programmers to have an idea of what that's about. And one way to do that is to learn a functional programming language and figure it out. So I'd encourage you to just have a go.
Actually,
it's really good fun.
I will at least read a book.
You definitely got to download an interpreter and download GHCI
and
so you
play
can
around.
You don't get it from reading a book. It requires a little bit of brain rewiring to learn a functional language. There's no two ways about it. You just have to think, all right, I'm going to spend a little bit of while rewiring my brain. But it's the most exciting thing since sliced bread, and I do think that this whole parallelism stuff is going to be important. That's one of my active research areas at the moment is nested data parallelism. I want to get data parallelism to work really well in Haskell.
Doesn't tell me much. Don't know.
The data parallelism is the way you're going to harness lots of processes.
Okay.
When you've got lots of data. Data
Mhm.
parallelism means do the same thing to every element of an array.
Right. Okay. Yeah.
But current when people say data parallelism today, they mean MPI and high performance Fivetran and Star C and indeed MapReduce, Google's MapReduce.
Right. Mhm.
And it's always flat data parallelism,
Mhm.
which is good for particular kinds of problems where you want to do something to every element of an aggregate, but the something is sequential. Nested data parallelism, an idea invented by a guy at Carnegie Mellon, or rather popularized by him, a guy called Guy Blalock is his name. So he showed how to take a program where you do in data parallel, you do to every element of an array, but the thing that you do is itself a data parallel algorithm, and that can do data parallel algorithms to any depth. So you get this recursive nested structure. That's much more widely applicable to a much wider class of problems, sparse arrays, graph algorithms, search algorithms, lots of computationally intensive, data-intensive algorithms. And what I'm doing at the moment is trying to take Guy's ideas and with colleagues in the University of New South Wales, lift them into the 21st century in the context of this already rather mature language, Haskell, so we can get nested data parallelism to work in the context of that language. So that's my current excitement.
Okay, very good. Thank you very much for being on the show.
Yeah, thanks for that.
Thank you. Thanks for listening to Software Engineering Radio. If you want more information about the podcast and all the other episodes, visit our website at se-radio.net. If you want to support us, you can donate to the SE Radio team via the website, or you can advertise for SE Radio, for example, by clicking on the Dig, Reddit, Delicious and Slashdot buttons. To contact the team, please send email to team@seradio.net, or if it's specific to an episode, please use the comments facility on the website so other people can read and react to your comments. This episode of Software Engineering Radio, as well as all other episodes, are licensed under a Creative Commons license. Please see the website for details. Thanks to Charlie Crow and the PodSafe Music Network for the music used in this show. The song is called Vegas Hard Rock Shuffle.